Hi, everyone. I'm Dan McKinsey and the host of today's colloquium speaker, Professor Brad Filippone from Caltech. So it's a great pleasure for me to introduce Brad. Brad will be talking about fundamental symmetry tests and parity violation precision measurements with free neutrons. I've known Brad, I think, for quite a while, sort of through the neutron connection. Brad did his Bachelor of Science at Penn State and his master's at Chicago and his PhD, his PhD at Chicago, and has been at Caltech essentially ever since. Now he is the Francis L. Mosley Professor of Physics. It's my pleasure to have him here today speaking about exploring symmetry violation with free neutrons. So if you have a question, just type it into the chat and I will call on and I'll repeat your question at a good opportunity.
Okay, thanks very much, Dan. I appreciate the invitation. I was originally scheduled, I think, March 28th, something like that. I was actually on the East Coast in South Carolina. We were on spring break and we were wondering, oh, maybe we'll just ride it out here when California was having issues. And then a week later, we said, we better get home. We may be there for months and months. So here we are. So today I'm going to talk about some work that I've been doing with free neutrons and this issue of symmetry violation. So I'll first discuss the discrete symmetries in particle nuclear physics. Why are they important / interesting? I'll talk about we need free neutrons to do the experiments. We'll talk about where they come from. I'm an experimentalist. We'll talk about these experiments. And then I'll talk about a number of experiments that my group is involved in. In one case, to look for the large parity violation, which we've known about for almost 70 years. In the weak interaction or electroweak interaction, there is a large parity violation that's observed. But since we can calculate that very precisely, you can look for deviations from what we call standard model of the weak interaction, and those could be suggestions for new physics at very high mass scales. And I'll also talk about another kind of discrete symmetry violation, that's time reversal symmetry. And we will probe that via electric dipole moments. So the discrete transformations or the discrete symmetries that we often talk about in quantum mechanics. First one is charge conjugation. You basically take a particle and turn it into its antiparticle. Parity flips the coordinates. So basically a vector turns into minus vector. And time reversal, you just reverse t. And the way it works in quantum mechanics is if the symmetry, that particular symmetry is conserved, then the Hamiltonian is invariant. So that if the Hamiltonian looks the same, time reversal, you operate with the t operator on the Hamiltonian, then a certain process, say particle A plus particle B interact and out comes particle C plus particle D, it means the reverse process is also completely calculable in the theory, and you can work it out. If the time reversed or the parity reversed or the charge conjugated reversed process doesn't exist, then that particular symmetry is violated. Originally, symmetries were viewed as a fundamental tenet in our understanding of basic particle interactions, and Eugene Wigner won the Nobel Prize in the early 60s for introducing them. But then it became quite interesting and important when discoveries, in particular parity violation, as I said in the 50s, was actually not conserved by the weak interaction. So we're going to talk about what I'm going to do is I'm going to first talk about the theoretical picture and sort of the theoretical / experimental picture in general, and then I'll focus on the experimental aspects as we move forward. So first one is parity violation in the electroweak interaction. So I want to consider the beta decay of a polarized neutron. And so here I have a polarized neutron. The neutron's polarization is the spin vector. It's an angular momentum, and so it's an axial vector. And so since a vector changes sign under parity, an axial vector does not. So when you operate on this picture on the left with parity, it becomes the picture on the right. The vector momentum of the electron changes sign, but the angular momentum does not. Parity symmetry would say both processes, left and right, are equally likely. If the experiment on the left does not equal the experiment on the right, then parity is not conserved. That's typically characterized by you can think of it as an angular dependence. Think of it as an angular dependence of a particle being emitted. Better here, yes. What angle, whether it's more likely to be along the direction of the spin or against the direction of the spin. And you can characterize that with an asymmetry, this alpha I've done here. So shortly after it was postulated by Li and Yang that parity might be violated because of some, there was something called the tau theta problem, which was having to do with particle decays. Two experimental groups immediately attacked it, both at Columbia, and they actually talked to each other. The one on the left was Wu et al. What they did was they had a nuclear beta decay, so much like the neutron, but it was a nucleus, and they polarized it by putting it into a fridge, a cryostat. So they got it cold, and they got it polarized, and then they looked for an electron coming out in a particular direction. So they set up a detector, and you look to see if the electron comes out. If you change let's initially polarize it this way and see how many you get. Then you change the polarization the other way and see how many detections you get. What they saw was, on the left is the counting rate when it's just pulled out of the cryostat. They had to pull it out of the cryostat so they could see the counting rate. And what you see is, as a function of time, the system warms up and the polarization goes away. So it's maximally polarized at t equals 0. So they pull it out and they see a higher counting rate when the magnetic field is in one orientation, and they see a reduced counting rate when the magnetic field is in the opposite orientation with respect to no polarization, which means warm. And they characterize that, they can actually measure that as an asymmetry. The difference, the amplitude of that difference is about 0.2 plus or minus 0.02. So that's a 10 standard deviation measurement of an asymmetry. That's what 5 sigma is enough to be a discovery. So they saw 10 sigma. A similar experiment was run with muon beam, Garwin and Letterman. The muon also decayed, and they looked for the detector was fixed, but the muon, when it stopped, before it was decayed, it was in a magnetic field, and depending on the muon's magnetic moment would rotate depending on the strength of the magnetic field, and so they would look at a fixed time how much it had rotated, and they varied that magnetic field until it rotated, as you can see, a full all the way around. And they plotted the count rate as they saw. And again, you see a 10 sigma measurement in terms of the amplitude of that asymmetry. And in fact, the magnitude of both asymmetries were consistent with the model that Li and that Yang had formulated. The second type of parity violation, or sorry, symmetry violation we'll be talking about here is time reversal symmetry. And we'll in particular consider an electric dipole moment. EDM is electric dipole moment. So you can imagine it for a neutron, or it could be an electron or a proton. The existence of an EDM implies time reversal invariance, and let's see why. So if I have a neutron with an electric dipole moment, so on the left is a dipole moment which points from minus to plus. It's presently along the spin. If I reverse time and the EDM was a true vector, then the EDM would stay the same, but the spin would flip. Okay, and so this particle on the left and the right are different. One has EDM up and spin up. The other has EDM up and spin down. Now you can make it by just rotating your head and looking at it upside down. You then notice that there are actually 4 distinguishable states for the neutron. There's a spin up and a spin down state with the dipole moment pointing either up or down. And so you're stuck with this quandary. I now have 4 possible states of the neutron, but we know there are only 2 distinguishable neutron states via the Pauli principle, so that if there is in fact observed an EDM, it must be due to a violation of time reversal. You can also see that it also violates simultaneously parity. I can give you a better, more quantum way of thinking about this. If you think about the Hamiltonian for a magnetic moment or an electric dipole moment interaction looks like this: mu dot B for the magnetic interaction, d dot E for the electric interaction. Let's now assume that we have a dipole moment. And so if only one of those states, like I showed before, is correct, then both the magnetic moment or the electric dipole moment will point along the angular momentum, as will the magnetic moment. And so the magnetic and electric dipole moments actually have the same symmetry as angular momentum, as J. I tabulate here how J behaves under parity. It's even because it's a axial vector. It's got a time component in it because it's a rate of change of the angular momentum is a rate of change, and so it's negative. And if you multiply these two things together, you can see that this term is even under parity because of the multiplication, and even under time, but this one is odd under parity and odd under time. So having both of them means that you're violating both time reversal and parity. You throw in the quantum field theory prediction or assumption that the product of the three discrete symmetries, charge conjugation, parity, and time reversal are conserved, then if time reversal is not conserved, then CP is also violated. That's interesting because CP violation potentially plays a big role in possibly resolving a big question in our observation of the universe. Apparently, if we look out right now, we see a dominance of matter over antimatter. Very little antimatter seems to still exist. So while early on you'd expect if you're starting with energy, there should be equal amounts. So where did it go? You could say, well, it's initial condition. Physicists don't like that. They like to be able to explain it in terms of their theoretical picture of the interactions. And Sakharov actually was able to explain it. He was able to, if the fundamental interactions possessed three properties, these are called the Sakharov conditions. The first one is that he didn't say quarks, but he said protons and neutrons. The baryon number, the proton number and neutron number must be able to change. And even the standard model at very high temperatures, which you have at the Big Bang, allows for a little bit of this, so that's okay. You need to be away from thermal equilibrium, or otherwise any excess of one over the other gets washed out by thermal equilibrium. But phase transitions are a way of getting out of thermal equilibrium. And lastly, you need both charge conjugation, C violation, as well as charge parity, or CP violation. It turns out, almost fortunately, the weak interaction violates both C and CP. However, the amount of CP in the actual standard model of the weak interaction is much too small to account for the baryon asymmetry. It's not big enough. And so there is a active search worldwide for new sources of CP violation that are larger than the known. The known CP violation was first observed in the 60s in kaon decay. It's a small effect, but important. It's part of the standard model. It's built in, and I'll show you in a bit later. And so there are lots of experiments looking for CP violation in other venues. In particular, recently there's been hints of CP violation possibly observed in neutrino oscillations. Hints meaning it's at the few, maybe 3 sigma level, and experiments are continuing actively there. There's also active searches worldwide to look for electron, muon, proton, and neutron electric dipole moments. Using for the electron, people use molecules. Atoms also have sensitivity. Atoms are also useful for looking at, atoms are made of neutrons and protons, so you can access proton and neutron. There's a discussion of a storage ring experiment for a proton looking for electric dipole moment, and then free neutrons. And I will focus on, since I'm going to talk about this technology of free neutrons, I'll focus on electric dipole moments for free neutrons. So I'm going to now switch gears from sort of the theoretical underpinnings of this symmetry violation to how do you do experiments. So what do you get free neutrons? The neutron is short-lived. It's not easy. There is some in the cosmic rays, of course, hard to do much with them. But you can produce lots and lots of neutrons in a reactor. In fact, it's the fundamental to a self-sustaining reaction of an energy-producing reactor. Every time you have a fission, you get a couple or three neutrons. So the neutron that comes in that's inducing the fission produces one plus additional ones. And so those neutrons can go strike other nuclei, induce fission, and you've got energy. The other way that researchers use to produce free neutrons is via accelerators in a process called spallation, where typically you have a proton beam on a large nuclear target, and you just rip the energy of the proton beam is quite high. There's lots of energy dumped into the nucleus, and the nucleus essentially falls apart. It produces smaller nuclei plus free neutrons and protons that are emitted. Typically, you get about 20 neutrons per breakup reaction, spallation reaction for a 1 GeV proton beam. And there are lots of facilities, we'll talk about facilities in a bit, that can do this. So how do you make a measurement with a free neutron? So we're producing neutrons either way. One interesting in this spallation case, the accelerator can control the proton beam, and so I can pulse it, and so I can have time information as well. So I know exactly when I'm producing the neutron, and that can be useful in some experiments. It's harder to pulse certainly a power reactor. Research reactors, in some cases, small ones do have that capability, but accelerators are good at making these pulse beams. So how do we study the neutron? How do we get our hands on these neutrons to do experiments? It turns out, well, if you think about if the neutrons are slow enough so that their de Broglie wavelength is large compared to the interatomic spacing in a solid. Say I have a solid and I have a neutron. In fact, if the neutron is coming at a glancing angle, then it's the de Broglie wavelength perpendicular to the surface that's important. And if the interactions of the neutron with the medium have the right sign and are the right magnitude, it's kind of like a mean field. The neutron sees many nuclei simultaneously. And so it acts kind of like an index of refraction for light. And in particular, since that effective potential that the neutron sees as it comes towards the surface, as we'll see, I'll mention in a bit, can be either positive or negative, you can have that the vacuum has a larger, or that the medium has a smaller, if you like, index of refraction than the vacuum. This allows you, instead of where light can be totally internally reflected, you can have neutrons that are externally reflected. And so there's a material here, the neutron then is reflected and continues propagating. That's how you make cold neutron beams. For very slow neutrons, there are something called ultra cold neutrons. That's when even a normal incidence, the neutron is reflected and turned around. And that only works for neutrons that are very slow, which I'll mention in just a second. So ultra cold neutrons, we call them UCN. You can actually trap them. You can trap them in a material bottle with vacuum inside, because the medium, the solid, acts like you're basically integrating over a lot of delta functions. And if the interaction, the scattering length, is for nuclei, the scattering length can be either positive or negative. The basic interaction is attractive, but an attractive short-range potential can have either positive or negative scattering lengths. If the scattering length is positive, when you integrate over all those delta functions, you get a step function. So it's just a 1D quantum problem. If the kinetic energy of the neutron is lower than this effective potential, often called a Fermi potential, then the neutron will bounce. There'll be an evanescent wave inside the solid, and if it's thick enough, there will be no propagation of the neutron. And so you can trap neutrons inside a material bottle. For both the cold neutron beam and for the ultra cold neutrons, you have to slow them down. So we need to take the neutrons that come from reactors or spallation. Both cases, they're MeV or tens of MeV, which is near the speed of like a few percent the speed of light. These are very fast neutrons. Their wavelength is very small compared to the solids. So you got to slow them down. Typically, that's done with some sort of moderator. If you have this MEV neutron coming into a material, now remember the neutron is seeing individual particles because its de Broglie wavelength is very small. So as it comes in, it scatters off these. The video is not great, but it's sort of bouncing off of all these nuclei, and so there's a recoil. And the lighter the thing you're bouncing off of, the more energy the neutron can transfer. And typically for appropriate radiators, you want appropriate moderators. You want the moderator not to absorb neutrons or have a small probability of absorbing the neutrons so that they just have elastic scattering. And in about 20 collisions or 100 collisions, depending on your moderator, the neutrons are slowed down to the temperature. They basically become in thermal equilibrium with the material, whatever material you're talking about. So at room temperature, it's a 40th of an EV instead of MeV. Slowing down takes about 100 microseconds, and the neutrons are now in thermal equilibrium. However, so if you have neutrons in thermal equilibrium, you have a Maxwell-Boltzmann distribution, and so there's a whole range of temperatures, and so you can pick out the slow ones and the really slow ones if you want. Okay, so let's characterize the kinds of experiments. So experiments are done with both cold neutrons and ultra cold. Cold neutrons typically have velocities of 200 to 1,000 meters per second. In contrast, ultra cold neutrons are never more than 8 meters a second. That has to do with the material, the density of the material, and the scattering length. And the best you can do is the highest velocity fully trapped neutrons are about 8 meters a second. An excellent sprinter can outrun the neutron in that case. Notice that also the dramatic difference in the de Broglie wavelength. You're about a nanometer for cold neutrons, and you're 50 to 100 nanometers for ultra cold. The corresponding temperature, so cold neutrons, actually, cold neutrons you can produce a fair bit with about 20 Kelvin. Going into thermal equilibrium at 20 Kelvin, you can get a decent amount. That's the corresponding velocity that is in thermal equilibrium with a 20 Kelvin moderator. Unfortunately, if you want to have 8 meter a second neutrons, they would have to be in thermal equilibrium with something at 5 millikelvin, which is really hard to do if you've got either a reactor or a high energy proton beam. Getting things cold is not trivial. And so for ultra cold neutrons, we have to do something else. Basically this is how you can trap the ultra cold neutrons are actually stored in bottles. We can store them in material bottles. We can also use the magnetic interaction. The neutron has a magnetic moment. We can use that magnetic moment to also confine it in magnetic fields that have a gradient. In fact, the other thing that influences ultra cold neutrons is gravity. Even the fastest ultra cold neutrons can only climb about 3 meters in gravity. And so we actually, in our experiments, we produce ultra cold neutrons. We actually make ultra cold neutrons accelerators by just having them drop a few meters, and they speed up dramatically. If the neutrons are even slower than 8 meters, then they only can jump a meter, half a meter. And that will become relevant in a bit when I talk about some experiments. So I'm summarizing the Maxwell-Boltzmann distribution for sources of free neutrons. If they are thermal, if you're getting your neutrons from a thermal distribution, Maxwell-Boltzmann distribution, this works reasonably well for cold neutrons because you can get a fair bit of cold neutrons in this range here at the low end of the 20 Kelvin moderator. But if you take the same distribution I show on the top and the same scale, 500, 5,000, 10,000, 15,000, how many per neutron velocity, and you extrapolate down below, now this is 8 meters a second, this is what's left. You see for a 300 Kelvin moderator, I calculate over here, only about 1 in 10 to the 8 neutrons is at the ultra cold neutron level, so you're going to get very few out. Even for a 20 Kelvin moderator, you only get about part per million ultra cold neutrons out. So how do you produce them? They were first produced at a reactor by actually using gravity. You take cold neutrons and you make them climb 20 or 30 meters above the reactor. Then gravity has slowed them down, and then you can extract them and try to do experiments. There's another trick, which was discussed in the 60s and 70s, and that's something called superthermal sources. It's super only because it sounds good. It's really, they're non-thermal. These are sources, these are moderators where you don't let the neutrons come in thermal equilibrium, because if you did and you wanted ultra cold, they'd have to be 5 millikelvin, which you're never going to keep. There are two what we call superthermal sources. One is superfluid helium-4. Superfluid helium-4 has this property on the right. What I'm showing is the dispersion relation. Blue is the excitations in liquid helium as a function of momentum of the excitation. And so it's phonons here, and out here it becomes rotons for the superfluid. And then if you simultaneously plot the neutrons dispersion relation, which is just p squared over 2m, the momentum squared over 2m, it's non-relativistic, obviously, you'll notice that they cross at a particular energy, which corresponds, this is like written energy in terms of absolute temperature. So this is about 11 Kelvin, they, which has that means a wavelength of about a nanometer. Such a neutron can collide with a photon and basically stop, because the two dispersion relations match. And so I can have a neutron change all of its momentum with a phonon and then stop. So I can rapidly slow them down. However, if those phonons are 11K are hanging around, then they'll make the neutron warm up again. They'll kick the neutron and make it fast again, and it'll escape. If you make the temperature of the system really cold, and what you need is less than 1 Kelvin, so that the chance of the neutron getting sped up and then kicked out of the trap is small, you need less than 1 Kelvin. The same technique also works with a moderator made of solid deuterium, which is something we developed a collaboration at Los Alamos Labs starting about 20 years ago. We use solid deuterium. The solid deuterium also has actually has many dispersion relations where phonons can be scattered by neutrons, and this allows we can produce ultra cold neutrons fairly quickly. This superfluid helium process takes some time for the neutrons to build up, and if you keep the temperature in the deuterium case below 4 or 5 Kelvin, there's a small chance of the neutrons getting we call it upscattering, which means they're too fast to be trapped anymore. And so this technology has now, some cases has been in use for 60 or 70 years. The reactors largely have been around for a long time. What I show here are, in red are the reactors, in green are proton accelerators. And so in the US, Canada, Europe, and Japan, there are a variety of sources. Essentially, all of these are taking part at some level in fundamental understanding the fundamental interactions of neutrons. However, that is not their primary goal, and I'll show you with a couple of I have a couple of examples. One of the oldest research reactors in existence is that's operating for science is the Institut Laue-Langevin reactor in Grenoble. This is a highly enriched uranium core reactor that produces a large flux of neutrons. You can then have moderators in here which slow them down. Here they have D2O, if you can see it. And so neutrons come out, like I said before, you can have these, if the neutrons come out at glancing angles, they can be confined, so you make a beam guide basically, and neutrons with the appropriate trajectory can be guided many, many meters. This is probably 30 meters here. And so each of these represents a beam line. And if you see, there's the circles are nuclear and particle physics, so those are the ones that are doing fundamental physics. There's two active ones, there's 3 active ones now, and there's a couple older ones over here that are doing that at the ILL. spallation type of a facility, an example is the spallation neutron source at Oak Ridge National Laboratory, which was commissioned, I should know this, 8 years ago, 10 years ago. It was built in order primarily because cold neutrons can have wavelengths of tens of angstroms or hundreds of angstroms. You can actually study lots of materials. You can study materials, you can study biology, you can study condensed matter with these neutrons, and that's their primary use. And so this is the facility. There's actually a proton accelerator way back here. All the experiments are here, and all this stuff up front is just offices and pretty meeting rooms. And so the guts of the facility is a cooled mercury spallation target and a set of cold moderators. In one case, regular cold helium, liquid helium is used. And so a proton beam comes in, and throughout many beam lines, cold neutrons come out. And this is their, if you go to SNS, the spallation neutron source, they'll show you where all their beam lines are. And if you can squint and read some of these, if you have a big screen, maybe you can see there are the things that they talk about are material science, even environmental science, life science, crystalline materials, condensed matter physics. So it spans the range from angstrom, 1 angstrom, which is close to what thermal neutrons are, all the way up to biological proteins can be studied for longer, slow neutrons that have longer wavelengths. And so this facility actually has one beam line, I circle there in yellow, that's the fundamental neutron physics beam line, which is used for this exploring fundamental interactions. Okay, let me tell you now a little bit about doing physics with free neutrons. So I'm going to talk about 2 kinds of experiments. The first one is the neutron decay, which uses the weak interactions parity violation, that symmetry violation I mentioned before. Since we understand the weak interaction precisely, if we measure it with sufficient accuracy, we can look for deviations from, we call it beyond standard model physics. We can look for beyond standard model physics. Both cold neutrons and ultra cold neutrons are used in these experiments. For a neutron electric dipole moment, we're looking for new sources of CP violation, as I mentioned earlier. These are mostly done nowadays with ultra cold neutrons. Initially, they were done with cold neutron beams. Those aren't competitive, although there's some ideas that maybe in the future they will be. They'll also be competitive. So I'll remind you, neutron beta decay. A neutron decays to a proton, an electron, an antineutrino. Its mean life is about 15 minutes for the decay, and it releases the energy. The summed energy of the final state particles is about 1 MeV. Remember, the mass of the neutron is about 1,000 MeV, 900 MeV. In the quark picture, we think about, and so this is the fundamental interaction point of view. The neutron has a UDD quarks. One of the d quarks is emitting a virtual vector boson, W minus, weak boson, and turning into a U quark. Then that virtual boson must decay, and it decays to an electron and an antineutrino. That's what's energetically possible, because the energetics is only less than 1 MeV. And so that's what it looks like in the quark picture. So how do you look for new physics? So the way you look for new physics is through these loops. Loops where the particles that are participating are very massive, and so it's a small probability, but if you have sufficient precision, you can see the signature of that loop being present. The example I show here is exactly the neutron beta decay, neutron going to a d quark going to an up quark in the same diagram I wrote before, and that can be directly related to a lepton decay, which is in this case a muon, which is simpler than a nuclear decay, where a lepton decays to a mu neutrino, an electron, and an antineutrino. The same coupling constant participates, so you can use muons to characterize that coupling constant. However, when you look at the quarks, it turns out that the the eigenstates, the basis states for freely propagating quarks are not the same as the weakly interacting eigenstates. And I'll show you there's a matrix that relates them. And so there's a matrix element that causes a change in this. And so that matrix elements you can extract by comparing this, the decay on the right with the decay on the left. Now imagine not only is the process, that simple weak interaction process on the top possible, but some new particles. This is an example from an old supersymmetry picture. These supersymmetric particles can also participate at some level, and they participate at a level that's proportional to the ratio of the masses, in this case, a logarithmic ratio. And so what you'll see is, if you don't know about these particles and you extract this VUD, it won't agree with the standard model, which doesn't have these particles, because it'll be modified by this correction term here. And so you're looking to see if there is a correction term, and that's the signature of a new massive particle. The relationship between them is that in the quantum picture, the weak eigenstates are on the left, the mass eigenstates are on the right, and there's a matrix called the Kobayashi-Maskawa, or CKM matrix, which relates them. And I was talking about this particular matrix element VUD. And this matrix can be constructed to explain that tiny amount of CP violation I mentioned earlier. Since it's a 3x3 matrix, there's a single complex phase, since it's a unitary matrix, that's possible. And that is the CP violation, the small amount of CP violation that's presently observed. So the neutron can provide, in principle, precise measurements of the neutron can provide the best measurement of VUD, which is a fundamental part of the standard model. And if you measure it sufficiently precise, you might be able to observe, say, a violation of unitarity. If the sum of the matrix elements, things have to sum to 1. If that doesn't work, you've missed some physics, meaning there might be new particles that are interacting. To use the neutron, however, you can't just use the neutron lifetime or the parity violating asymmetry like I talked before. You need to use both, because the weak interaction has a vector part and an axial vector part. That's because it's violating parity, so it has both a vector and an axial vector part. And the axial vector part in a neutron, the quark's axial vector coupling is modified by being stuck inside a strongly interacting ball of neutron. And so by measuring two independent properties, the neutron lifetime and the parity violating asymmetry, you can extract VUD and GA separately. And so you can measure them both. However, this sounds great theoretically. There is a bit of a problem. The neutron lifetime, the experimentalists aren't cooperating yet in terms of a precision value for the neutron lifetime. It turns out over the past 30 years or so, there have been two techniques. This cold neutron technique, which is this red line. This is cold neutron beams. So a cold neutron beam, what you do is you have a neutron zipping by, and you have a detector, and you count how many protons that neutron produces as it zips by, and you can figure out what the rate of decay is. Ultra cold neutrons, shown in the blue, what you do there is you trap them inside a bottle and you store them for 10 seconds, 50 seconds, 1,000 seconds. And every time you empty the bottle, you see how many neutrons are left, and you watch how they decay. And so you can measure a lifetime. The two disagree by almost 10 seconds. And so that's a pretty bad, big, large uncertainty on something that's 1,000 seconds long, compared to other particles, which are measured part per million lifetime, like the muon. In fact, never second guess particle theorists. This problem has been around for a while, and a couple of theorists suggested that perhaps the neutron doesn't only decay to a proton, an electron, an antineutrino. There might be a window, and they demonstrated there could be a window for some sort of dark matter particle that is produced, that is making the lifetime look longer for the beam than for the bottle. And so obviously some experiments, in fact, you'll see one of our experiments was attacked one of these proposed processes and basically ruled it out with our experiment. So that's the lifetime. We are involved. My group is involved in a collaboration called the UCN Tau experiment at Los Alamos. This is kind of fun. As you can see, it's a bathtub-sized trap. The bottom of the trap is loaded with permanent magnets that are oriented in different directions. It's called a Halbach array. The orientation is such that it produces large gradient. It's sort of, if you actually look at the field of a refrigerator magnet, it has that similar property where the direction of the field very locally is changing rapidly. This produces a large gradient magnetic field. That gradient magnetic field allows you, if you pick one spin state of the neutron, one spin state is attracted to a gradient, the other spin state is repulsed. We call it a low field seeker or a high field seeker. So you take polarized neutrons. If you inject into this system low field seekers, they will stay away from the bottom of the bathtub. So the bathtub is shown here on the left. You can see this funny shaped bathtub. That's sort of to mix up the trajectories. Oops. There we go. And so the neutrons can't touch the surface. They just bounce from the surface because of the magnetic gradient. And if they bounce too high, if their energy is too high, they escape from the trap. They can climb over the edge and disappear. And so we only trap neutrons that are slow enough that gravity doesn't let them escape. And so we store them. We clean out the ones that are at the top. We lower an absorber. And then we store them for, in fact, we've stored them. Remember, the lifetime is only 15 minutes. We've had neutrons stored in this thing for an hour and a half. And when we empty it, we still see neutrons, ultra-cold neutrons still in there. So the way we do it, we have this black detector here. We call it a dagger. I think it should be called a guillotine, but it's not big enough probably, but it's more like a dagger. So we drop it at the end of the storage, and all the neutrons that are bouncing around up and down, it has a strong absorption probability. When neutrons absorbed, it produces an alpha particle in the nuclear reaction of the absorption. That alpha particle produces scintillation, and we see a light signal. The light signal is then sent to these two photomultiplier tubes. And so in about 10 seconds, all the neutrons that are bouncing around in the trap, remember, even the ones that are at the top have to come down eventually. And so after a period of about 10 to 20 seconds, we stop seeing any counts, and so we can count all the neutrons. We do this for a variety of different times, and we can measure a lifetime. This experiment published their first result a few years ago using this apparatus with an uncertainty of about, it was actually on the plot I showed you on the previous slide, uncertainty of about 0.7 seconds statistically and systematic is the uncertainty, so less than a second. We'd like to eventually get to maybe 1/10 of a second. We have new data that is presently blinded, which has seems to have a statistical sensitivity of 0.3 seconds and a systematic uncertainty below that level. And we are anxiously hoping to unblind that and release that result soon. In fact, I have a graduate student with a job waiting for him at Goldman Sachs in New York next year. And so he's hoping to finish his thesis and get a final result. So we're in the process of comparing data from 3 different analyses to decide when we're ready to unblind. And so that result will come out soon. So the experiment you have to combine that with in order to extract the weak interaction parameters. You also need an asymmetry. So just like the asymmetries we talked about before, it looks like 1 plus a coefficient times cosine theta. In this case, the coefficient is multiplied by V over C. Beta is V over C for the electron. And we're looking for the asymmetry of the electron coming out of the decay with respect to the neutron spin. So I'm showing little neutrons polarized that way in my picture initially. And so they're in a big solenoidal magnetic field. We can flip the neutrons spin this way or this way. And we have 2 detectors at either end, the N- and the N+ detector. And the electrons that are emitted are captured by the solenoidal field, and they spiral around, and either hit this detector, no matter what. If they're emitted facing the detector or up to plus 90 degrees or minus 90 degrees, it will go to one detector. If it's larger than that, it will go to the other detector. And so we just take the number of counts plus and minus, take the difference over the sum, and that's the asymmetry. That asymmetry can be directly related in the weak interaction to this axial vector coupling constant. And so we can extract that and then use the lifetime as well to measure things like the UD quark-weak coupling. And so that experiment has also recently published data. This is just it probably won't work well in Zoom, but this is a cartoon that shows you the source here is solid deuterium. I'll produce a green ultra-cold neutron, which will bounce around. It will go through a couple of magnets which polarize it. It's then inside this long solenoid until the neutron decays. It emits a neutrino, which is disappeared yellow. And then blue is the electron, and the electron is either counted on the right or the left once we measure the asymmetry. So that result was published a few years ago. At the time was the best measurement of the neutron's parity violating asymmetry. It turned out, in that case, remember I mentioned the first observation was a 10 standard deviation measurement of the asymmetry. This result is a 250 sigma measurement of parity violation. The error bar is so small compared to the magnitude of the asymmetry. And that's because we're looking for these physics beyond the standard model. We need to make precision. This level of precision gives us sensitivity to mass scales that are about 1,000 times heavier than the proton mass. So instead of 1 giga electron volt, it's 1 tera electron volt is the sensitivity of these experiments. And we've also published a couple of other experiments having to do with beyond standard models, something called Fierz interference, which is a new kind, a possible new kind of scalar interaction. And we also looked, as I mentioned, for this dark matter decay. Our detector was ideally suited to look for neutron decaying to dark matter and an electron and positron. In some cases, the electron and positron will go in opposite directions, and we could easily see that in our experiment. We didn't see it, and we ruled out a large part of the parameter space. Let me finish. The last experiment I want to talk about is the neutron electric dipole moment and where new physics can be observed there. As I mentioned several times, the standard model of the weak interaction, there is a small amount of CP violation in this matrix, the CKM, Kabibo, Kobayashi, Masukawa. This produces an electric dipole moment. However, the standard model dipole moment is in units. The dipole moment is a charge times a length. And so 10 to the minus 31 e centimeters, which is the unit we always use. The best sensitivity, the best measurement to date says it's got to be less than 10 to the minus 26. So there is something like 5 orders of magnitude, almost 5 orders of magnitude, where there is no standard model, and any EDM you see is new physics. So if you can improve the limit compared to this, the same is true for the electron standard model EDM is even smaller than this. And so there's a range where you can study new physics by looking for electric dipole moments. And where they can come from, again, a massive particle, in this case, a supersymmetric particle. The magnitude of the CP violation depends on the 1 over the mass of the particle. So the heavier the mass, the smaller the EDM, but this allows sensitivity up to tens, 50, in some cases, hundreds of TeV for electric dipole moments. And so they are potentially sensitive to physics beyond what's studied at the Large Hadron Collider or even the next Large Hadron Collider. So just to set the scale, an electric dipole moment is a charge times a length. So for the neutron, what should it be? Well, let's just separate the charge by, say, if it's 1/10 of the radius of the neutron, you have a length, you have a charge, 2/3 and 2/3, plus and minus. You get 4 times 10 to the minus 14 e centimeters. You just plug in the numbers. Remember that the best measurement we have says the EDM for the neutron is less than 10 to the minus 26. So it's smaller than this. So the size of the EDM in terms of the separation of the charge is ridiculously small. We often say it's like measuring the thickness of a human hair, and the neutron is the size of the Earth. That's sort of the scale. So the searches for the neutron EDM were begun actually at Oak Ridge National Lab with one of the first reactors. That was actually the reactors studying them for both military and power reasons in the 40s and 50s. And so they were searching, actually, since I said EDM violates parity, the Purcell and Ramsey were looking for a violation in parity. And so their first experiment, they actually looked at old data in 1950 and published their own experiment in 57. And in order to do this, you're basically processing the neutron. You're trying to measure a frequency, and I'll show you, I'll give you a little toy in just a second. You want to measure a frequency very precisely. Both of these people won a Nobel Prize for magnetic resonance, not in the same year, quite a few years apart. But they developed this idea of using magnetic resonance to measure a frequency with fantastic precision. The sensitivity, so if you want to measure what's relevant for doing a better experiment on electric dipole, in order to get, this is the error bar as a function of experimental parameters, you want to have a high electric field, you want to watch the particle for a long time, that's TM, the measurement time, and this square root is how many times you do the measurement, you repeat the measurement, you win like the square root of the number. Also how many neutrons or how many particles you have per measurement, you win by the square root. So simplified measurement is you inject a polarized particle inside an electric and magnetic field. You flip the spin of the particle, and it will have a magnetic moment, if neutron, proton, or electron, so it begins to precess. You now flip the electric field and see if that precession is quicker, which on my screen is quicker, but because of the baud rate, it's not. It looks, you can't tell, it looks kind of quicker. So you just flip it back and forth from parallel to anti-parallel, and you look for a frequency shift. And so, of course, there's a big, if the magnetic field varies, the frequency that you observe can change, so you have to be very careful about monitoring the ambient magnetic field in order to see this very tiny effect due to the electric dipole moment. So if I want to do a better experiment from existing experiments, how do I increase the statistical sensitivity? I need more neutrons, I need a higher electric field if possible, and I have to make sure systematic effects don't dominate my, uncertainties in the end. Just to give you a picture of where things stand in the world, I said this is a very active field. Many of those facilities I showed you earlier are now using these super thermal UCN, ultra-cold neutron sources that have been developed in the last 20 years to do electric dipole moment experiments. And so I have a bunch here. The present limit in units, I'm using 10 to the minus 28 centimeters, is 180. In those units, this is the level of sensitivity for future experiments. And I will talk about this one here, which is less than 3 in those units, the smallest uncertainty, which is our NEDM at SNS experiment. So I will discuss that briefly and then wrap up. So the experiment is at the spallation neutron source. It was a concept proposed in the 90s by Bob Gollum and Steve Lamoureux to do a cryogenic experiment. So we do a cryogenic experiment. In fact, we use, if you use superfluid helium, that the super thermal source to make high density of neutrons, we can produce 100 times more neutrons than have been used previously. Since I've got helium, liquid helium anyway, I can use that as an insulator. And we've already demonstrated we can get more than 70 kilovolts per centimeter compared to the previous experiments which were done in a vacuum of about 10 kilovolts per centimeter. We also have techniques to monitor systematics. These other tricks are systematics. And we believe that in a 3 calendar year run, we would have a sensitivity of 3 times 10 to the minus 28 centimeters. So that's nearly 2 orders of magnitude over the present experiment. The collaboration is shown here. It's a fairly big collaboration. There's something like 70 active members from a variety of institutions and national laboratories, so universities and national labs. We recently published a detailed technical design of the experiment in Journal of Instrumentation. We are now actively building the components for this experiment. And so just to let you see what's the trick, how do we measure the frequency in our case? So we inject both polarized neutron and polarized helium-3. Remember, I've got superfluid helium-4. I can put polarized helium-3 in there. I can rotate both their spins And the helium-3 has a slightly larger magnetic moment, so it rotates a little bit faster. And as it rotates, sometimes the spins are anti-parallel and sometimes they're parallel. It turns out when a neutron and helium-3 spin are anti-parallel, there's a huge probability that they capture, and that the capture products are energetic proton and triton. Those two particles deposit energy in the superfluid helium that produces light. We use that light signal. We see an oscillation in the light signal to measure the frequency. We flip the electric field to see a different frequency. If it's correlated with the electric field, it's a signature of an electric dipole moment. You should ask, the helium-3 is behaving like it's got two protons that are paired off, so it looks like a free neutron. In fact, it's only 10% different in its magnetic moment, so it has an electric dipole moment, but its electric dipole moment is shielded by its atomic electrons. The atomic electrons around helium-3 prevent the nucleus from seeing the electric field that we apply. The experiment is at this spallation neutron source, which is actually by the time we run, it'll probably be 2 megawatt power, beam power, 1 GeV proton. Proton beam comes here from the right. The experiment is actually here. I'll zoom in. There's a truck to sort of give you the scale just outside the door. So the experiment involves polarized helium-3 being produced up here, injected into the experiment. There are magnetic fields and internal magnetic shields. This region in the middle is all cryogenic. It's 1,500 liters of superfluid helium in the middle. Cold neutron beam comes in from the left. I can zoom in. The business end of the experiment are 2 storage cells where we store the neutrons. Are produced by a cold beam entering the superfluid, scattering off of phonons, slowing down the neutron stops or becomes very slow. And then we have a high voltage terminal in the middle, produce either electric field plus voltage or minus voltage, produces opposite electric field in the 2 cells, and the magnetic field is always pointing in one direction. So you can actually see an EDM signal from the 2 different cells. Experiments are actively under construction. We're building the magnetic system, magnetic field and cryogenic shield at Caltech. You can see sort of the scale of a person. We have this large region, this high bay area in what's called the synchrotron lab, a synchrotron that turned off in the 1960s. We still call it the synchrotron lab. And the magnet system, we will finish our subsystem first and be at Oak Ridge, hopefully end of next year to start commissioning it. Our system will be commissioned first, polarized helium-3 next, and the high voltage and central cell afterwards. So we won't be able to start data for about 4.5 years. And I'll show you, this is where we hope to get. This is the published neutron electric dipole moment sensitivity as a function of time. You see we're on this very steep curve early, but lately it's sort of been flattening out. And we hope with much higher electric fields and higher neutron densities, we can speed that up. And let me finish. I have this fun picture to sort of illustrate the energy scales we're talking about. So on the left, I'm talking about the LHC and the next LHC. This is 10 to the 14 electron volts. The Higgs boson is here. You can see neutron decay is here, neutrino rest mass. Way over here, if you ask what's the energy that we're measuring, the electric dipole moment is the energy is D dot E. For the sensitivity that we're talking about is 10 to the minus 23 EV compared to 10 to the 14. You've got 10 to the 37 range of energies you're probing to look for the same physics. You're looking for physics at the very high energy scale. And to steal a quote from a former colleague of mine, there's plenty of room at the bottom. In this case, the bottom is at the low energy side. So I would like to take this opportunity to thank funding agencies and my collaborators and my research group for allowing this research to become real. And I also want to thank you for your attention.
Thanks, Brad. I'm going to use the virtual clap. Express our appreciation. And if you have questions, go ahead and use the raise hand function. I'll call on you. Yes, Pablo.
Yeah, you mentioned that you could make a UCNA detector specially suited to detect dark matter. How do you do this?
Yes, I think I can quickly. I'm going to go back to the detector. So the theorists proposed a bunch of possible decay channels. So it should be right here. Okay, one of their proposed decay channels was that the neutron decays to a dark matter particle plus an electron and a positron. That's a three-body decay, and so depending on the energetics, the electron and the positron sometimes will go in the same direction and sometimes they'll go in opposite directions. So what we did was we looked for a fast coincidence between this detector on the left and this detector on the right. Normal beta decay, we only see a signal on one side, either the left or the right, but we're seeing a simultaneous signal in both sides, and that was a way to look for it. It's a funny story. We said that, the paper came out, and then a week later we had our data. We had our data already. Can we see this? So the graduate student went to look for a coincidence between the two sides, and he saw nothing. And I said, there's got to be some background. There's got to be something. He got nothing. I said, look at the code, and the code said, oh, if you see one in both sides, ignore it because it can't be real. It can't be our physics. So it basically turned, the analysis routine said, oh, ignore those because they're not part of our data. And so we turned that off, and then we saw background, but not much. We did see a few coincidences, but they were consistent with backgrounds not from neutron decay.
Okay, thank you.
Questions? Yes, Nicholas.
Perhaps I do not understand, but shouldn't they only arrive at the same time if the actual point of decay is at the very center of your device? If they're positioned closer to one of the two edges, won't they arrive at a different point in time?
But it's still, yes, that's correct. But that deviation in time is measured in nanoseconds. In fact, the neutrons are not filling this completely. They are actually confined from about here to about here. So what we would see, so you could see a 5 or 8 nanosecond difference if it hits one versus the other, but the probability of from background of seeing a coincidence, even so, either it's simultaneous or within 10 nanoseconds, is extremely small. So we took that whole range, as you say. Yes, we have to. It could have occurred anywhere inside there, and we did include that wherever the decay could have occurred. But they're essentially moving nearly relativistically, the electrons.
Thank you.
Cynthia? Cynthia Kasu?
I think you're muted.
Oh, hi, Shord.
It doesn't show muted. Cynthia, you have a question?
Oh, I'm sorry, I'm muted here. Yeah. Could the axion act as a dark matter particle for this, since you've got parallel electric and magnetic fields in your apparatus, and that's what I often see for axion detectors?
So, in fact, for the electric dipole moment search, these experiments are being used to look for a time-varying axion signal. So you look to see if your electric dipole moment signal is oscillating, and that frequency is related to the mass of the axion. We're actually, yes, we're looking at how we could improve in our experiment the sensitivity. And in fact, we're a little bit different. We are continuously measuring the frequency over a few periods, and so we will have a different frequency sensitivity. All the other types of experiments require you to have the neutrons precess for 100 or 200 seconds and then extract them. And so the smallest time interval they can study is sort of that 200 seconds. We can study a few seconds, or even, we're rotating at 100 hertz, so probably 100 millihertz we could move to. And so we will have different enhanced sensitivity compared to the existing experiments.
I was wondering, Brad, do you have any suspicion for the source of the discrepancy between the bottle experiments and the beam experiments, or what's your?
Well, I vote where my feet are, and I'm working on a bottle experiment, but we haven't yet. And there is the good news is there's another bottle experiment with much higher precision. And the worst case scenario is they still disagree by 10 seconds. Well, maybe then you start wondering about new physics. I'm not ready to say new physics. There's still lots of systematics that are possible. If neutrons are escaping from your trap in the trap case, you get too short a lifetime. If you're not counting all the protons, you're getting too long a lifetime through some efficiency. And so the experimenters are trying to remove this. In fact, there's some experiments that are trying to do both simultaneously. They're trying to look for, say, electrons from the decay, as well as the number of neutrons left after you store them. And so there's an experiment called Probe at Los Alamos that's trying to simultaneously measure, so that the systematics of the experiment at some level might be the same, and the systematic effect might disappear, which a lot of us suspect there's some systematic effect.
Thanks. Evan?
Hi, can you hear me okay?
Yes.
Yeah.
All right. Well, I was actually going to ask the question that you just basically answered about trying to do the beam in the bottle experiment simultaneously.
Right.
But just as a kind of a tangent to that, for the bottle experiments, how well do you need to know how many neutrons you have at the beginning of the of your time sequence in order to get that decay lifetime?
What you have to know is you have to know a number proportional to that. You don't have to know exactly, because what you can compare how many are left after 20 seconds to how many are left after 1,000 seconds. But that's only if you know that you put the same amount in. Okay, we don't actually have to know the number. We have to know that it was the same. So we have this normalization question is key. And so what we do is we check that. We have separate monitors that monitor the number of ultra-cold neutrons that are being transported into our system. And so we use that because what can change? What can make the number that get loaded different? We use a proton beam. If the proton beam changes, that can change if the deuterium changes. So what we do is we look at, say, every time you store for only our shortest time is 20 seconds. So you develop a normalization scheme such that the spread of the corrected number that you unload is minimized. Then you've developed a good normalization. That number should always be the same. If you for a given number of neutrons you put in, which you can scale with these other detectors, you should get the same number out. And so you use these tricks. And so a large part of the analysis is making sure you can correctly scale the number of neutrons that you loaded every time, that you can correct for the fact that it won't be the same every time, but you have a monitor of how much it's not the same.
So, well, how much does that contribute to your systematic error?
We're still trying to characterize. It's probably going to be, that's probably going to be a half to 2/3 of our systematic error, I suspect. A lot of the other systematic errors, like the neutrons that are orbiting around near the top, can last a long time. But we do simulations, plus we do measurements where we put an absorber and try to clean at different. You change the spectrum of neutrons that are in there and see if you get the same answer. And so we use those things. So that, I think that's also a systematic, but I think the normalization to me has always been what I've told my graduate student is focusing on that. That's likely to be the dominant systematic.
Okay, thank you.
Sherwood?
Yeah, just a basic question going all the way back to your introduction, talking about CP violation in explaining matter antimatter asymmetry.
Right.
Do we need CP violation in both the hadronic sector and in neutrinos? And are there any other source of CP violation that we might expect to look for?
So it's possible there's something, so there's there are two popular ways of characterizing it. Baryogenesis is hadronic, is quarks, and then there's leptogenesis, where the neutrino sector, CP violation in the lepton sector could map into the baryon sector through B minus L interaction. And so the lepton asymmetry would turn into a matter. Matter is the quark, so that's what's, we're characterizing it. So it could be either, and so we have to look at both. There's the question is if it's big enough, you have to also, in the neutrino case, even if there is CP violation, it doesn't guarantee that there is leptogenesis. Same thing for electric dipole moments, and so you need the theoretical input as well. And the exciting thing for the electric dipole moments is we have lots of different handles. If we measure the electron, electric dipole moment, and the neutron, and the proton, and other systems, which one has an EDM and how big it is in each case tells you what the underlying physics is, what the source of it is. That's the interest from the new physics point of view. Any kind of CP violation is important for the baryogenesis, for the matter-antimatter asymmetry, as long as it's big enough.
Thanks.
I see no further questions. So thank you, Brad, for a very interesting talk. And let's all thank Brad using the clap function, if you can find it. It's under the more thing. Here we go.
Thanks very much. I enjoyed it. It's different, but it's always nice to come visit Berkeley, which I didn't get a chance, but next time, sometime in the future.
We'll find it another time soon.
Yep.
Thank you, Brad.